Welcome to Lyons Township High School, Physics C. Got an example involving statics. Net force and net torque equaling 0 on the system. So the system today is a pretty simple one. It's our bicep. We're going to figure out if you're holding your backpack in your hand, holding your forearm horizontally, and your upper arm vertically, so a 90-degree angle, how much force approximately, and everything we're going to do today is approximate, how much force your bicep has to, how much tension your bicep has to apply in order to hold that backpack up. So we're going to model your arm the following. You've got the upper arm and then the lower arm. That's your elbow. This would be your shoulder joint, and here would be your hand. Okay, and the bicep, we're going to do a really simple model. We're going to say, hey, it's kind of like a diagonal line. It's attached 7 inches above your elbow and 2 inches from the base of your elbow. So the one attachment point's right there. That's about 7 inches. And then from here to here is about 2 inches. Now, again, these are all estimates, but it gives you a pretty good idea how big these forces are. The two weights we're going to worry about is your actual forearm itself. We're going to simplify that and say it weighs about 5 pounds. And then you're holding a 20-pound backpack or dumbbell in your hand. Okay? How much force does your bicep have to exert to hold those two things up? Turns out it's going to be a lot more than 25 pounds. So I'll give you a couple dimensions here. From here to here is 2 inches. From here to here is 3 inches. And then from here to here is 7 inches. Okay, in other words, we're kind of saying the center of mass of your forearm is a little closer to your elbow than it is to your hand. Okay, which is probably about right. So we're going to do this, and we're going to do a couple things here. Since it's a static situation, you're not moving anything. We know the net force in any direction we choose is 0. We also know the net torque about any pivot we choose is 0. Okay, so I'll start with an FBD. We haven't really drawn an FBD. It's just a sketch. Okay, we're going to draw an FBD of just the forearm from this point to that point, from your elbow to your hand. So if we do that, I'll kind of expand that out a little bit. Okay. Okay, so we have the 20-pound backpack, no problem. We have the 5-pound forearm, no problem. By the way, we're not drawing these to scale. We have the bicep pulling up at an angle. We'll call that tension. We're trying to find that number. We also, if that was it, your forearm would go flying this way. So we have a horizontal reaction force. Your upper arm holding your forearm in place. I'll represent that with an F sub x. That is also going to have a vertical component, an F sub y. A lot of textbooks will call those Rx and Ry. That's fine, whatever you want. We have to guess. Now, I hope Fx is pretty plain. The tension's pulling left. This force has got to pull right. Okay. Now, if you didn't guess right, if you guessed outward, that would be fine. You would just get a negative value, and the number would be correct. It would just be a negative sign in front of it. For F sub y, same thing. We're going to make a guess, and if it's wrong, then you'll just get a negative value, but the value, the magnitude is correct. So now I kind of know which way it's supposed to go, but I'm going to pretend like I don't and just say, hey, we're going to say up. We're going to say it points up. So here's my guess, F sub y. And again, if we're wrong, we get a negative value, but it's the right number. Okay. All right. So we're going to basically come up with 3 equations. We got 3 unknowns here. We don't know the tension, we don't know Fx, and we don't know Fy. So we got to come up with 3 formulas. Oh, and by the way, I'll quickly mark. This is 2 inches from there to there, 3 inches from here to here. So obviously, the picture ain't to scale. And then this here is 7 inches. Okay. We're going to need that angle. Okay. So that angle, going back to over here, that's this angle here. It's just inverse tangent of 7/2. So the angle is inverse tangent of 7/2. which ends up being about just over 74 degrees, 74.05 degrees. We got 4 sig figs in there. But actually, here's what I'm going to do. I know that tangent of that angle is 7/2. Okay? I know that sine of that angle is opposite over hypotenuse. The hypotenuse is root 7 squared plus 2 squared, which is root 49 plus 4. The hypotenuse is root 53. So sine of that angle would be 7 over root 53, and cosine of the angle would be adjacent over that, which would be 2 over root 53. I'm just going to use those. Whenever I need a sine, cosine, or tangent, I'm going to plug those in. And then we'll get reasonably accurate numbers that way. All right, so we'll start with, that's math, okay? We'll start with net force in the x direction is 0, okay? The horizontal direction. Well, that's really simple. If you look at this diagram, assuming right is positive, you got fx to the right, you got the component of tension pointing left, which would be t cosine of that angle. So it looks like this. You've got fx minus t cosine of that angle, and that's it. So that equals 0. So we got one equation for our 3 unknowns. We still need 2 more. The next one will be net force in the y direction is 0. Okay, now there's a little more to that. Assuming up is positive, we've got Fy pointing up, and we've got the component of tension pulling up, T sine theta. Downward, we have the 5 and the 20. So we would write Fy plus T sine of my angle minus 5 minus 20 equals 0. Okay, so there's our second equation. We still got 3 unknowns, so now we got to go to net torque. So if we do net torque, about some point is 0. So you can pick any point, okay? And no matter which point you picked, you'd have a third equation with the same 3 unknowns you'd be able to solve. As per our discussions in class, there are points that are more convenient than others. Typically, you want to look for a point where the most unknowns go through it. So in our situation here, 2 of my 3 unknowns go through the elbow. So we're going to do a net torque about the elbow. If we do that, Fx and Fy, they create no torque about the elbow, so we can now ignore them. So we still have the tension trying to pull this thing counterclockwise. You have the weight of the forearm trying to pull it clockwise, and you have the backpack weight trying to pull or rotate your system clockwise. So we'll go with, in my work, I went ahead and did counterclockwise is the positive direction, okay? So if I do net torque about the elbow, I've got the tension providing a positive torque. That's trying to spin your arm counterclockwise. So for this one, what I did was I said, well, we need the component of the tension that's perpendicular to this 2-inch radius. That's really simple. It's just T sine theta. That's the component of tension that's perpendicular to your forearm. So we've got the tension, sine of theta, times 2 inches. Okay? And by the way, we're doing everything in pounds and inches. As long as you leave all your units in pounds and inches, that's fine. Then we have the forearm weight, which is a minus torque. It's trying to rotate your system clockwise. That's 5 pounds times, that's 5 inches from the elbow. And then you got the backpack weight, which is also clockwise torque, or negative in our system, and that is 12 inches from our elbow. And that all equals 0. Well, the cool part about doing net torque about that axis is the only unknown in that whole entire equation is the tension. Okay, you got everything else. So if you do this, I will do one line of algebra just for kicks. So we've got t times, and we know the sine of the angle up there is this, okay, and then times 2, minus, that's 240, and that's 25, so that's 265. So actually, and I'll move that over to here, so that equals 265. So our tension is going to be 265 over 7 over root 53 times 2, okay? And I mean, if you put all the numbers in your calculator, I got about 138 pounds. Now, again, I want you to make a note of that. The backpack and the forearm combined only weigh 25 pounds. Your bicep has to apply 138 pounds of tension to hold that up. So it turns out the muscles in the human body are really strong. They apply large forces. The reason that force has got to be so big is because the lever arm is so small. And to bounce out these torques, you got to have a big torque. Now, by the way, that's also why, for instance, when you bend over, they always tell you bend your knees and lift with your legs. If you bend over, your back muscles have a very, 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 very small lever arm, and they have to apply huge forces to pick something of weight up. And that's how you can hurt your back. So don't do that. So anyway, there's a tension in the bicep, and then once you've got that, you plug that back into here to get your FX. When I do that, I got FX was 37.9. Okay, so that's how hard your elbow, when you're doing this, your elbow has to push this way with just about 38 pounds of force. And then also, if you find Fy, it turns out you get a negative value. And by the way, when you find Fy, again, you just plug in T into there. Okay, so you plug T into there and solve for Fy. You get, I got negative 108 pounds. Okay, so what does that mean? It just means we guessed wrong. And the reaction force for the elbow, this force has to point down. If you kind of look at it, and if you know ahead of time that tension is going to be pretty big, then the bounce, your vertical force, that force has to point down. So when you're holding up something heavy, your forearm is actually pushing down very hard, or your upper arm is pushing down very hard on your forearm to hold it in place. So hope that example is helpful. Some just quick notes. Always be careful about your angles. In this problem, to find the torque created by tension, you have two options. You can find the amount of that force that's perpendicular to that radius, or if you wanted to, you can find the shortest distance between the elbow and that line of force, which would be about there. If you did that, you're still going to get cosine of the angle or sine of the angle in there, so it doesn't really matter which way you do it. So in this example, to me, it was easier to find the perpendicular component of the force to the radius. And also, again, be very careful of direction. And lastly, if you don't know the direction of a force, just guess. And if you guess wrong, no big deal. You just get a negative value, and that just means you guessed the wrong direction, but the magnitude of the force will be correct. So hope that was helpful. Thank you very much.